Am I audible?
Yes, sir.
Okay, thank you. Yeah, how many are there? Shall we start or should we wait for the other students to arrive? We'll wait for some 5 more minutes. Okay, I think we can start. And yes, till now, what you have seen is the narrow band fading, right? So we saw, mm, yeah, we saw what narrow band fading is, and we saw the properties, that is Ri and Rq components are Gaussian, and we saw the statistical properties, autocorrelation, mean, cross correlation, and we have seen some theorems, Wiener-Khinchin theorem, central limit theorem. Yeah, and we have seen what a WSS process is, and we have seen uniform scattering in the environment and zeroth order Bessel function. Okay, now coming to the like what we have seen is the reason for finding this Bessel function is to first find the autocorrelation, then take the Fourier transform, then we'll get the power spectral density, then we'll proceed to calculation of power. Right? First we have to find the autocorrelation, then take a Fourier transform, then we'll get power spectral density, then integrate it, then we'll get the final power. Right? So the diagram here shows the power spectral density, right? So you can see the equation over here on top of the diagram. Yeah, you can see this equation SRIFF and SRQFF. These represent the power spectral density. Okay, so you can see this equation, that is 2pr by pi fd into 1 by root 1 minus f by fd whole square. Okay, so what you can see here is, if frequency f, if f is equal to fd, right? If f equal to fd, what will happen? If you can see the diagram, if f is equal to fd, f by fd is equal to 1, right? If f is equal to fd, f by fd will be 1. So what will happen if f by fd is equal to 1? What will happen to the power spectral density equation? Denominator
Infinity,
will
sir.
be, yeah, denominator will be 1 minus 1. That will be 0. So that will shoot to infinity, right? The equation for power spectral density will be infinity when f by fd is equal to 1, right? If f is equal to fd or f by fd is equal to 1, denominator will be 0. That means the power spectral density will be going towards infinity, right? Yeah, now I would like to point some changes that I have seen in some materials. So in Andrea Goldsmith textbook, you can see that the equation for power spectral density is, I mean, the term associated with the power spectral density is 2pr by pi fd. But I have seen some changes in some materials by foreign universities like UC Davis or something like that. So what they have done is they have changed this term associated with the power spectral density. That is, instead of 2pr by pi fd, they have given the term as pr by 2 pi fd. Okay, so yeah, having said that, we'll be coming to the receipt power. So this equation is corresponding to the in phase and quadrature component, that is Ri and Rq. That is the first equation corresponds to in phase and quadrature component. Now what we are doing is we are finding the power spectral density of the received signal, that is R of t. So in first equation we found the power spectral density of in phase, in phase and quadrature component. But in second equation, what we are trying to do is what we are trying to find is the power spectral density of the received signal, that is R of t. So power spectral density S R of f is equal to 0.25 into SRI of f minus fc plus SRI of f plus fc. So the question now is, how is it f minus fc and f plus fc? Can someone answer this?
Sir, it's because the whatever signal we have, that's band pass, I think, a band pass, it's centered around the carrier frequency. That's why we do this.
Uh, can we look at the mathematical steps instead of saying carrier frequency, etc.? Yes, it is related to the carrier frequency, but why is it f minus fc and f plus c? Because the reason is, see, here we have found in first equation we have found SRI of f and SRQ of f. That means we have found the we are calculating the power spectral density related to the in phase and quadrature component, right? And now we are trying to find the power spectral density related to the received signal. Okay, having said this, we are going back to the equation. Yeah, equation 6, the one in the bottom, equation 6. So a, what I'll do is yeah, can you see this equation 6? That is a r of tau is equal to a r I of tau into cos 2 pi fct plus some term which will be 0, right? So A R of tau is equal to autocorrelation term into cos 2 pi FCT. So right now what we did is we found the power spectral density corresponding to the in phase component. That means we took the f of t of A R I of t, right? So we have the autocorrelation component and we have the Fourier transform as S R I of f, right? Now we have to multiply the autocorrelation term with cos 2 pi fct, and we are going to see what is the effect of multiplying the autocorrelation term with cos 2 pi fct. So the effect of multiplying something in time domain with cos 2 pi fct is, yeah, so if you multiply x of t with cos 2 pi fct or cos omega 0 t, what will happen? So let us say that x of t is something in time domain, the signal in time domain, and the corresponding frequency domain signal is x of f. Okay, now x of t is multiplied with cos omega 0 t. What is omega 0? Omega 0 is nothing but 2 pi f0. So after multiplying x of t with cos omega 0 t or cos 2 pi f0 t, we'll get the frequency domain version as 1 by 2 into x of f minus f0 plus x of f plus f0. So we are making use of this property. We are taking this property to this equation. That is SRI of f was there, and we are having f minus fc here, and we are having f plus fc here, right? And we are making use of this 1 by 2 in the amplitude also. And remember, I have some doubt regarding this 0.25. In it would have been something like 0.5, right? It would have been something is c. If SRIFF, if SRIFF was the frequency, I mean power spectral density of the in phase component, it would have been 1 by 2 in the amplitude term. But instead of 1 by 2, that is instead of 0.5, what is given is 0.25. Anyway, we'll see why it is like that. Uh, so the equation can be written as PR by 2 pi FD into 1 by root 1 minus mod f minus fc by fd whole square. So we can rewrite the equation like this. Okay, now what we are doing is we are trying to find the power, right? So in order to find the power, see if you see this diagram, we have the Doppler frequency in relation with the theta, in relation with theta. So FD is plotted with respect to theta, and the Fourier transform of FD of theta is plotted, which is the power spectral density. And from power spectral density, what we can do is we will be finding the power, right? So what I wrote here is we know what is theta, and from theta we can draw what is the PDF of theta, and then from the diagram we take the Fourier transform and we will get the power spectral density, right? So what we are doing is we are plotting the PDF of f of theta, and then we'll be plotting the power spectral density, which looks like this. So this is the time domain version. The first one to the diagram to the left is the version in the time domain, and the diagram towards the right is the one in the frequency domain, right? So we have fd of theta to the left, and we have sriff to the right, and these are the Fourier, Fourier transform pairs, right? Okay, now you can see the diagram to the left, that is fd of theta, which is plotted with respect to theta. See, what we are doing is we are plotting fd of theta with respect to theta. So instead of plotting the the dark line, what we are doing is we are converting the dash line, I mean the dark line to the dotted lines. So if you can see, instead of a continuous line, what we are trying to do is we are making the continuous line to straight lines, the dotted lines, which looks something like this. I'll change the color of the pointer to, yeah. So if you can see, it looks something like this. Instead of continuous line, it is a straight line near zero. I mean, just after zero, and then it's a straight line with some slope, and afterwards it is coming something like this, and then again it is a straight line. So instead of a continuous line, we have converted the continuous line to a set of straight lines. Okay, so in the right side we can see the corresponding power spectral density. So we can see that uh, yeah, we can see that towards, in frequencies FD and minus FD, you can see these areas FD and minus FD. So in FD and minus FD, the frequency domain component has the amplitude near infinity. In FD and minus FD, frequency domain components have amplitudes near infinity. And why is it so? Can you give an explanation why the amplitude of power spectral density shoots up to infinity when the frequency is at FD and minus FD? The reason is there are multiple components here. If you can see this area, if you can see the area in this rectangle, there are multiple components here. See, there are multiple components which are getting added up, and because of this multiple components, we are having something, some amplitude which is near infinity. It may not be exactly infinity, it is going up to infinity. And similarly, in FD, the similar thing is happening. In FD, there are multiple terms, multiple theta terms that are getting added up. Similarly, here also, near 2 pi also, there are multiple terms that are getting added up. Therefore, in Fourier transform, we are having the amplitude that tends to infinity at frequencies FD and minus FD. So if you see the figure to the right, you can see at FD and minus FD, at FD and minus FD, since multiple components are getting added up, we are having amplitudes towards infinity. Okay, so the idea is we are analyzing why we have uh, why the power spectral density is going high when it comes to FD and minus FD. Okay, so the next question is that how we can simulate narrowband channel. How can we simulate narrowband channel? So the answer to this is we know some properties. We have seen some properties. That is, we have seen that in phase component and quadrature component of the received signal, that is Ri of t and Rq of t, are independent and they are Gaussian also. Gaussian in the sense that the uh, yeah, you will be having a curve that look like this. A bell curve will be there when you plot f of theta with respect to theta. Okay, so this is the Gaussian curve. Yeah, and remember, when you plot Gaussian curve, it should not touch the x-axis. Most of the people, what they do is they'll be drawing the x-axis and they'll touch the x-axis something like this. So this is wrong. It should go, as x tends to infinity, it should appear like a parallel line. It should go like this. It should never touch x-axis. And similarly, towards minus x also, it should appear like a parallel line. Okay, so what we have said is there are two components, that is in phase component and quadrature component, and they are independent and Gaussian. Therefore, we can use an LPF, that is low pass filter, to model in phase and quadrature component. Okay, we can use LPF to model in phase and quadrature component. And what we are supplying to the LPF is a noise with the power n0 by 2, right? We are supplying noise with the power n0 by 2 to the low pass filter, which is having the gain as h of f whole square. The gain as h of f whole square as the gain. Okay, so how can we relate these two terms? Why do we need low pass filter, and why are we supplying n0 by 2 as the input of low pass filter to make narrowband channel? See, the question is, why are you giving noise source as an input to the low pass filter to generate a narrowband channel? Because the answer is, it is the noise is AWGN. The noise has the distribution that is Gaussian, right? We have studied that noise is AWGN, that is additive, white, and Gaussian. Additive, white, Gaussian noise. So noise will be having the distribution like a normal curve or a Gaussian curve, right? So that we can supply noise to the low pass filter with power n0 by 2, and the output will be Gaussian, right? So we'll be having a narrowband channel using LPF filter, and the input to the LPF filter will be n0 noise with power n0 by 2. Okay. Okay, so now you have seen this diagram in multiple textbooks, maybe in previous chapter, right? Maybe Tanvir sir has covered this. Maybe the first two portions, that is path loss alone and shadowing plus path loss, and you are going to see why it fluctuates. Like, see, there is a good amount of fluctuation, something like this, right? It's not a straight line. It's not a straight line, and there is a good amount of fluctuation when you are adding multipath. So the first case was path loss alone. Second case is that you are adding shadowing to the path loss. And now what you are trying to do is we are adding multipath to the shadowing and path loss. And because of multipath, we'll be having a random fluctuation. And see, you can see that random fluctuation here. And what we are plotting is power versus distance in linear mode. We are plotting power versus distance in linear mode, right? So one more thing to be noted is that the power is normalized. The power is normalized. So what do you mean by normalized power? The answer is that we are bringing the average power to 0 dB. We are bringing average power to 0 dB. So if it is not normalized, what will happen is the power would have been something like 1 dB, 2 dB, 3 dB, something like that. So in order to make it to some standard structure, what we are doing is that we are bringing the power to 0 dB, right? So we have the normalized power plotted with respect to the distance in a linear scale. So if you can see the diagram to the left, there are random fluctuation that goes up then goes down, and there are some portions something like this. So we'll be zooming some areas, some particular portion. So the zoomed area is to the right? So you can see some at some portion we'll be having the graph that is going up, and then again going down, and then again going up, right? So the distance between two different, what do you call it, positive peaks, we can call it as a positive peak or something like that. So the distance between two positive peak can be something like zero point 0.4 lambda, or half wavelength, or half wavelength. So the advantage of this setting is that if the antenna spacing is somewhat like half wavelength or zero point 0.4 lambda, we can separate out the individual components. We can separate out the individual components. So if it is not zero point 0.4 lambda, what will happen is the yeah, what is it? Yeah, the diagram would have been something like it shoots up, then something like this, some, some random graph. So let us say that the distance is zero point 0.2 lambda or something like that. So there is no separation. There is no separation, or there is some good amount of correlation between these two spots. So if there is a correlation, if there is no independent nature between these 2 points, the data that is coming out of these 2 points will be same, and we do not want that to happen. We want independent data uh, from these 2 points, right? Then only we can separate out two different copies of data from these 2 points. If the copies of data are same, then there is no advantage. So we want different copies of data from different points, and in order to have different copies of data to different points, we must place antennas at half wavelength. Then only we'll be having independent nature of the channel. Okay, so why do we have this fluctuation? Why do we have this random fluctuation? Why is it so? Why is it random and fast? And the answer to that is, we have written the narrowband equation. We have written the narrowband equation, that is R of t is equal to real part of u of t into e raised to j 2 pi fct into summation of alpha term and e raised to minus j phi n term. So the idea is that multiple paths are getting added up here, right? Multiple paths are getting added up. That is, a transmitter is there, receiver is there. Since it is narrowband, we are adding multiple paths, right? And there is a single delay. So we are adding all these paths together, right? So that is being represented by this equation, that is summation alpha n of t into e raised to minus j phi n of t. So because of this addition, because of the effect of amplitude and phase difference in these individual paths that are getting added, we are getting random fluctuations. Got it? Since we are adding multiple components, multiple paths that are placed together, we are having only one path at the end, right? In reality, it is only one path. But since multiple paths are getting added, we will have to consider the effect of amplitude and phase associated with these individual paths. And because of this addition, we will be having random fluctuations. Are you getting it? It is because of this individual components that are getting added, we'll be having random fluctuations. Okay, now comes to the, we are coming to some important terms, that is Rayleigh distribution, then exponential distribution, etc, etc. So yeah, we'll be seeing the distribution, envelope distribution and power distribution of a channel. So let us say that we have two components, right? We have discussed that we have two components, that is in phase component of the received signal and quadrature component of the received signal, Ri of t and Rq of t. Now what I am doing is Ri of t I am writing it as x and Rq of t I am writing it as y. So we are writing z which is equal to root of x square plus y square. Z is equal to root of x square plus y square, or z is equal to root of ri of t square plus rq of t square. And there is a name for this particular equation, that is, it is called as the envelope of r of t. Okay, so the property is that if x is Gaussian, or if ri of t is Gaussian, and if rq of t is Gaussian, then z will be Rayleigh. The envelope of r of t will be Rayleigh. That is, if ri of t is Gaussian and if rq of t is Gaussian, then the envelope of r of t is Rayleigh. So we term these kind of channels as Rayleigh channel. And remember, we will not be having any LOIS component in Rayleigh channel. Okay, we have Ri of t square plus Rq of t square, and we take a root, and then it is called as envelope of R of t, and then such channel is called as Rayleigh channel. And one more thing to be noted here is that Rayleigh channel is a channel where we do not have any LOS component. Okay, so we can write the distribution as Pz of z, which is equal to 2z by Pr dash into e raised to minus z square by Pr dash. Okay, which we can write it as z by sigma square into e raised to minus z square by 2 sigma square. So this is the PDF of Rayleigh channel. Okay, this one is the PDF of Rayleigh channel. Okay, so if you are told to simulate a Rayleigh channel, what will you do? What is the immediate step to be done? You need not go for the PDF of Rayleigh channel. You can simulate it using you can generate it using by creating a Gaussian Ri of t and a Gaussian Rq of t. You need not consider Rayleigh channel, Rayleigh PDF as such. Okay. Now we'll see what is the power distribution. Okay, we'll see what is the power distribution. So Z is equal to, that is R of t is equal to root Ri square plus Rq square. Now what we are doing is we are finding the distribution corresponding to the power. That is, we are finding the distribution corresponding to Z square, which is equal to 1 by Pr dash into e raised to minus x by Pr dash, which is equal to 1 by 2 sigma square into e raised to minus x by 2 sigma square. Right? So this particular equation is called as, this distribution is called as exponential. So this distribution is called as exponential, right? So I'll just brief the entire steps. So we have Ri of t, which is Gaussian, and then we have Rq of t, which is Gaussian. And if you take the envelope of R of t, that is Z of t, it is Rayleigh. And if you take the power of R of t, the distribution is exponential. Is it clear?
Yes, sir.
Yeah, so there are different kind of distribution that are coming to the picture. Gaussian, and then we came to know there is something called as the Rayleigh distribution. Then we saw exponential distribution, right? So envelope is Rayleigh, power is exponential. Power is having exponential distribution. Always remember these things. And remember, Rayleigh channel is a channel where we do not have any LOS component. Now we will see what will happen if we have an LOS component. Yeah, and before that we can attempt a small problem. Okay, so yeah, okay, let it be there. So you can consider this question. Consider a channel with relay fading and average received power PR dash is equal to 20 dBm. Find the probability that the received power is below 10 dBm. So you have a relay fading channel, that is there is no LOS component. So you know that envelope is relay, power is exponential distributed, right? And find the probability that the received power is below 10 dBm. How will you do that?
So we will integrate the PDF from 0 to 10.
Second, just a second. Yeah, we will integrate
The probability distribution function from 0 to 10.
any other answer? See, the question is we have a relay channel. A relay channel in the sense that the envelope is having relay distribution, power is having exponential distribution. Now, listen carefully. We are having envelope which is having relay distribution, power is having exponential distribution, and Ri is having Gaussian, Rq is having Gaussian distribution. Now, find the probability that the received power is below 10 dBm. Find the probability that the received power is below 10 dBm. Yeah, so what is the first step? See, what is the question here? You tell me what is the question here. Find the probability that the received power is below 10 dBm. So what kind of distribution is to be used here?
So it's the exponential one.
Why is it so?
Because you're talking about the power distribution, right?
Yeah, we are talking about the power distribution. We are not talking about envelope, and we are not talking about the Gaussian distribution. We are talking about power distribution, right? So the question is to find the received power that is below 10 dBm. So even though the question starts with relay fading, etc., etc., the PDF to be used is exponential distribution, right? The PDF to be used is exponential distribution. Why is it so? Because envelope is having Rayleigh distribution, power is having exponential distribution. So what is that equation? 1 by PR dash into e raised to, what is that equation? E raised to minus x by PR dash, right? X by PR dash. So this is the equation of exponential distribution. Right now, what are the additional data we require? What is PR dash here? See, PR dash is equal to 20 dBm. So 20 dBm is corresponding to The 20 dBm is something in log scale. So this is in log scale, and we have to convert it into linear scale. So the linear value corresponding to 20 dBm is 100 milliwatt. So we can write the probability. I mean, the equation for probability is, I mean, as 1 by 100, 1 by 100 into e raised to minus x by 100, and we can integrate from 0 to some value. See, the question is to find the probability that received power is below 10 dBm, below 10 dBm. So this is also in log scale, right? This is present in log scale. We have to convert this log scale to linear scale, to linear scale. So what is the value of, the value corresponding to 10 dBm in linear scale?
Sir, it's 10 milliwatt.
It is 10 milliwatt. Okay, so yeah, so what we are trying to do is we are trying to integrate 0 to 10, and the PDF is 1 by 100 into e raised to minus x by 100, and once we integrate we will get this value. Are you getting it? Can you please check?
Yes, sir, I'm getting it.
Okay, so uh, if we see the pictorial representation of what we are trying to find, we have the PDF, that is, this is the exponential distribution, which is the power distribution. We are trying to find the total power below 10 dBm. So this is the power at the x-axis. So the total area below 10 dBm is is the value that we are trying to find. So this is the area that we are trying to find. The area of the curve under, below 10 dBm, right? So if the question is to find the probability that the received power below 20 dBm, then what would have been the change? If the question is to find the probability that the received power is below 20 dBm,
Sir, our integral limits would change. We would go from 0 to 100.
uh, anybody other than Yuvraj? No one else? Mm, anyone else? Asta is there? See, if you don't answer, I'll do one thing. I'll give attendance to Yuvraj only. Is it fine? Can you hear me?
Yes, sir.
Yeah, can you please answer? The question is, okay, if you haven't heard the question, if the question is to find the probability that the received power is below 20 dBm. See, now what we found is the probability that the received power is below 10 dBm, right? Now, if the question is to find the received power below 20 dBm, then how can we write the equation? See, the one that you are trying to find is the area below some particular value, right? Probability that the received power is below 10 dBm or below 20 dBm or below 30 dBm. That means we are trying to find the area of this, the area till this point, right? Till this point, if it is 20 dBm. Or if it is 30 dBm, we are trying to find the area till this point. So the question is to find the area till 20 dBm. And the answer will be 0 to 100 and 1 by 100 into e raised to minus x by 100 dx. Am I right? Do you agree with me? Okay.
Yes.
Yeah, thank you. And now what we are doing is we are adding LOS component. So till this point, what we have covered is a channel without LOS component, which is called as relay channel. Now we are adding LOS component, and such channel is called as Rician channel. Okay, if you refer to some textbooks, you can see some spellings as RICIAN, and some may write it as RICACEAN. Both are fine. I think this is more accepted. Okay, now the distribution can be written as Z by, the distribution can be written as Z by sigma square e raised to minus Z square plus S square by 2 sigma square into I0 Zs by sigma square. And we can have the received power as PR dash is equal to 0 to infinity Z square P of Z, which is equal to two components. There are two components, right? Which is LOS component and NLOS component. That is S square plus 2 sigma square. So if you compare these two equations, you can see that there is a particular term that is getting added, that is S square term. Earlier, if you see this equation, you can see that this equation, you can see that equation of P of Z is equal to Z by sigma square e raised to minus Z square by 2 sigma square. There was no S square term, no addition term was here, right? So what we are trying to do is we are adding the LOS component. That is, we are adding a plus S square term to the PDF. So received power is equal to S square plus 2 sigma square, where S square corresponds to the LOS component and 2 sigma square corresponds to the Rician factor. And we can write the Rician factor as, see, when it comes to the Rician channel, the important term associated with Rician channel is the Rician factor, which is K. K is equal to the LOS power divided by NLOS power. Right? Are you getting it? The main term, that is main parameter corresponding to the Rician channel, is the Rician factor. That is K, which is equal to S square by 2 sigma square, which is again equal to LOS power by NLOS power. Okay, so what is the idea, that what is the physical significance of K? What will happen if K is high, or what will happen if K is low? See, what will happen if K is high? You tell me what will happen if K is high.
Sir, it means there is more power in the LOS component.
Yes, there is more power in LOS component and there is less power in NLOS component. That means that the direct path from transmitter to receiver will carry most of the power, and the multipath, the reflected path, will be carrying lesser power. So if K is less, what will happen? If K is less, what will happen? That
More
means
power
N.
is distributed
Yes,
in the
yes.
reflected.
Yeah, almost all the power uh, is taken by this NLOS components, right? Taken by the multipath, so that the LOS power is less significant. The line of sight component is less significant, and most of the power is taken by multipaths. That is the reflected paths. Okay, now we can also write this equation. The last two equations are the probability density function in terms of K. The first equation and the last equations are same. Only difference is that we are writing the equation in terms of K. That is the Riccian factor. So as I said, when you say that channel is Rician, we can say we can specify the PDF of the Rician channel in terms of Rician factor, that is K. That is what is shown in the last equation. That is the PDF of channel in terms of K, that is in terms of Rician factor. So we have seen two channels, one is Rayleigh channel, another is Rician channel. Rayleigh means there is no LOS component, Rician means there is LOS component plus multipaths, right? So Rician does not mean that we have only LOS component. Rician means that we have also an LOS component. Okay. Now there is another distribution which is called as Nakagami distribution. So the PDF can be written as what you can see, that is 2 raised to 2 into m raised to m into z raised to 2m minus 1, then a gamma function, gamma of m, then average power raised to m, e raised to minus m into z square by average power. So the why are we speaking about this Nakagami distribution? See, we have everything in Rayleigh and Rician, right? We are talking about a LOS component and non-line of sight component. And if there is no LOS component, we can say that it is Rayleigh channel. And if there is no, I mean, if there is a presence of LOS component, we can say that it is the Rician channel. So why do we need Nakagami? The idea is that it is more general channel. Means based on m value, based on the value of m, it can accommodate Rayleigh channel and Rician channel. That is, if you put m is equal to 0, the probability density function will be equal to the Rayleigh channel. And if you put m is equal to k plus 1 square by 2k plus 1, then the channel will be Rician channel. Similarly, if you put m is equal to infinity, then there is no fading. Right. So the important parameter that is associated with m, I mean with Nakagami is m, which is the fading parameter. Right. So depending on m, we can say that we can predict the nature of the channel, which is it Rayleigh, is it Rician, and is there any fading, etc. So we have seen Rayleigh channel, we have seen Rician channel, we have seen Nakagami distribution. So Rayleigh channel means there is no LOS component. Rician channel means there is LOS component, and there is something called as a Rician factor, which is represented by K, where K is equal to LOS power by N LOS power, right? So Rician factor means there is some term associated with Rician channel, that is the Rician factor. And the third one is the Nakagami distribution. So the parameter associated with Nakagami distribution is m. So depending on m, you can say you can explain the characteristics of the channel. That is, if m is equal to 0, it is Rayleigh. Then if m equal to k plus 1 square by 2k plus 1, it is Rician. If m is equal to infinity, it is no fading. Okay, now we can solve some problems. Okay, and I have some three problems. Yes. So the question is, we have a channel. We are not talking about narrow band or wide band or anything, right? We have a channel with center frequency 850 megahertz, and it is a four tap channel. It is a four tap channel with delay 201 nanosecond, 513 nanosecond, 819 nanosecond, and 1223 nanoseconds. That is, these are the tau values. These are the tau values, that is tau 0, tau 1, tau 2, tau 3, etc. And similarly, we have amplitudes alpha 0, alpha 1, alpha 2, alpha 3. And the question is to find the received signal. Can you please try? So what is the equation for R of t? So you can write R of t is equal to real part of summation. See, the basic equation is given here on top of the slide, this one, and we can also write it as alpha I e raised to j 2 pi fc t minus tau I into u of t minus tau I. You can write it like this, right? So we can write the baseband signal as baseband. Baseband means we are removing the carrier frequency term, and we can write the baseband received signal as summation. We are removing the real part also. Summation ai e raised to minus j 2 pi f c tau I into u of t minus tau I. Okay, and you have to add I is equal to 0 to 3. There are four channels, right? There are four paths. So you have to start from I equal to 0 and travel through four different paths. So this is the equation. Now you please find the received signal. Find the received signal. So how will you draw the power spectral density? No, sorry, not the power spectral density, the power delay profile. Power delay profile which explains the behavior of the channel. So we can have two different axes. This is the x-axis which shows the delay, and here it shows amplitude in dBm. So we'll be having different tau values, different components, right? One, two. How many are there? There are four components, right? One, two, three, and four. So this is tau 0, tau 1, tau 2, tau 2, and tau 3. And the amplitudes associated with this is alpha 0, alpha 1, alpha 2 and alpha 3. Right. So this is the explanation of the channel. This is the power delay profile of the channel. Now you write the equation of the received signal. So what is the component? First, how will you write the first path? I mean the component that is received from the first path. What is alpha 0? Alpha 0 is 1, right? 1 into e raised to minus j 2 pi into fc. What is the value of fc?
850 megahertz.
Why is only Yuvraj Jain who is talking? What about other people? Yeah, let me see who's talking. So yeah, what is FC value? Aravi Prashant Kulkarni, can you please mention the value of FC?
850 megahertz.
Thank you. And then who else? Sheikh Ashar Afros. Value of tau 0. You people feel bad when you say the answer. Why is it so? Okay, so e raised to minus j 2 pi fc, that is 850 into 10 raised to 6, right? Into value of tau 0. Tau 0 must be added, that is where is that? Yeah, 201 into 201 into nanoseconds, that is 10 raised to minus 9, right? And this is to be multiplied with u of t minus tau 0. Tau 0 is 201 into 10 raised to minus 9, right? Plus this one corresponds to the which path? What is the path number here? This one corresponds to path 0. Now we have to write equation for path 1. So what is the equation for path 1? For that you will need alpha 1. Alpha 1 is nothing but 0.6. 0.6 into e raised to minus j 2 pi 850 into 10 raised to 6 into what is tau 1? Tau 1 is nothing but 513. 513 into 10 raised to minus 9 into u of t minus 513 into 10 raised to minus 9. This is path 1. And you need, what else do you need? Path 2. So what is the equation for path 2? Tell me.
0.3 into e to the power minus j 850 into 10 to the power 6 into 819 into 10 to the power minus 9
819, yeah.
into
Into
u
u
of
of
t minus
t minus 819 into 10 raised to minus 9. Correct. And path 3, that is fourth path. Yes.
So
Anyone else?
0.
0 point?
0.2
2, yeah, into
times the exponential of 2 pi times 8
6 into
into 1223
Yeah. 10 raised to
into 10
minus
to the
9
power
into
minus 9
u of
u of
t minus
e minus 1223 into 10 to the power minus 9.
minus 9. Yeah, that's it. So now you can use your calculator and tell, see, you can represent these values as some complex number. This can be one complex number, and this can be another complex number, and again this can be another complex. So you'll get four different complex numbers into u of something. So can you find the value of these complex numbers and tell me? Hello. ശരി. ക്ലാസ് എടുത്തണ്ടേ. ശരി. Yes, is it solved? What about the first component?
Sir, is it 0.993 minus j times 0.1135?
These are the values that I saw in a textbook. 0.59 plus J 0.81.
Okay, sir.
Can someone confirm? Are you getting it?
So first one is correct.
Okay. Okay, in that case, then the others will also be right. So the first value is 0.59 plus J 0.81. Second is 0.57 minus J 0.19. Then third 0.18 minus J 0.24. Last one is minus 0.19 plus J 0.06. Right. So yeah, this is how you find the received signal. So each component has some amplitude factor, and each component has some a delay component. So this is how you find the received signal. Okay. Now we'll see another question. So this time we have two different settings. That is, let us consider first setting. That is, we have a two tap channel, which means L is equal to 2. We have L is equal to 2. So what is meant by two tap channel? We have the power delay profile, something like this. So there are only two components, right? We have A0 component and we have A1 component, right? So yeah, you have the delay and you have the amplitude factors. You have the delay, that is A0 is equal to 1, A1 is equal to 1, and tau 0 is equal to 0, tau 1 is equal to 1 by 2 Fc. Can you find the received signal? Do the same thing. See, here you found the received signal, right? from the amplitudes and delays. Do the same thing. So what is the equation? Sigma alpha I e raised to minus j2 pi f c tau I, right? And we are assuming narrow band assumption. We are having narrow band assumption, which means that there is no u of t minus tau 1, no u of t minus tau 2, etc. So there is no u component here. We have only sigma ai e raised to minus j2 pi fc tau I. Okay, so now find the received signal. So the equation will be something like this, that is alpha 0 e raised to minus j2 pi fc tau 0 plus alpha 1 e raised to minus j2 pi fc tau 1. So what are the values for alpha 0 and alpha 1? Alpha 0 is equal to 1, that is 1 into e raised to minus j2 pi fc into 0 plus alpha 1, that is 1 into e raised to minus j2 pi fc into tau 1. What is tau 1? 1 by 2 pi fc into, sorry, 1 by 2 fc, 1 by 2 fc. So can you simplify this and tell me the value? E raised to 0 is what? E raised to 0 is, what is e raised to 0?
1.
1. Then plus, that is the first component. Then plus f2fc and 2fc will be cancelled, and what remains is e raised to minus jfc, j pi, e raised to minus j pi. So e raised to j theta is equal to cos theta minus j sin theta, which is equal to cos pi minus j sin pi. And cos 180 is what? 0. So what remains is cos pi, which is equal to minus 1, right? Cos pi is minus 1 or plus 1?
Minus 1.
Yeah. So what remains is 1 minus 1, right? Which is equal to 0. So what kind of, what is the inference from this example? Can we say this example as an example of
Destructive interference.
destructive interference is, I don't think interference is the right term, but it is destructive. It is called
Destructive
as,
addition.
yeah, addition. Now do the same thing with a small difference. We have the delay as 1 by fc. We have the delay as 1 by fc. Okay, so what will be the answer? A0 e raised to minus j2 pi fc tau 0 plus a1 alpha 1 e raised to minus j2 pi fc tau 1, which is equal to e raised to minus, it will be 0, right? Plus alpha 1, that is 1 into e raised to minus j 2 pi fc into 1 by fc, which is equal to 1 plus e raised to minus j 2 pi. Simplify this thing, e raised to minus j 2 pi. It is equal to 1 plus cos 2 pi plus j sine 2 pi, right? So j sine 2 pi will be 0, right? Cos 2 pi. What is cos 2 pi? 1. So answer is 1 plus 1, that is equal to 2. Again, since it is not 0 and we are getting an additional component, right? We are getting, see, the initial term was 1. What is get, see, we are transmitting some signal. Let us say we are transmitting 1 and it is passed through a channel and it is received here with um, an amplitude alpha 0. Similarly, another channel has some effect alpha 1. So we have some kind of addition here. So this one can be treated as an example of, what is it? Constructive addition, right? So there are two examples, and the first one is destructive addition, second one is constructive addition. So what was the main difference between the first example and second example? In the first example, the second component has the delay of 1 by 2 fc. When in the first example we had the second delay as 1 by 2 fc, and the second example we had the delay as 1 by fc, right? That is the only change that you can see in these two examples. Instead of 1 by 2 fc, it is 1 by fc. And look what happened. The first one had no output. The received signal is equal to 0, and we have experienced a destructive addition. But since we had the second delay as 1 by fc, we are having an added term, that is a constructive addition. Okay, so this is the important observation that we have to make. Even though we are standing in a particular place intact and we are not moving, because of the delay of the multipath, we may get the signal and we may not get the signal depending on the components, depending on the delay or amplitude, etc. Right? So yeah, this is one example of destructive and constructive addition. Yeah, we'll see the last example. See, if you look at these values, these are the same equation and same values corresponding to the question 1. Right? We have seen the same values. Tau 0, tau 1, tau 2, tau 3, amplitudes 1, 0.6, 0.3, 0.2. Same values. Only difference is that find the received signal with a narrowband assumption. With a narrowband assumption. And what do you mean by narrowband assumption? There is no u of t minus tau terms. Narrowband assumption means there is no u of t minus tau 0, u of t minus tau 1, etc. So what we are trying to find is sigma alpha I e raised to minus j 2 pi fc tau I, right, into some u of t term, into a u of t term. Yeah, now please find the received signal. Yes. So what is the difference here? Look at the first question. Look at question 1 and please tell me the complex number that you got for different paths. Path 0. Path 0, path 1, path 2, path 3. See, we had a complex number and then u of t minus tau 0 or u of t minus tau 1 and u of t minus tau 2 etc. in question 1, right? See, if you look at question 1, you had a complex number corresponding to alpha I e raised to minus j2 pi fc tau I, and that you are multiplying with u of t minus tau I. So the difference here is that you are assuming a narrow band. You are assuming that the channel is narrow band. Therefore, you won't need this u of t minus term in the equation. So what you have to find is this complex number alone. You don't have to add u of t minus tau 0, u of t minus tau 1, etc. with individual parts, right? Now, please tell me the complex numbers associated with each parts. Because of alpha 0 and tau 0, what is the complex number?
0.587 plus 0.809J.
0.59 plus 0.81, right? J 0.81. 0.59 plus j 0.81, and for path 1, that is because of alpha 1 and tau 1, we have uh, we have 0.57 minus j 0.19. We have 0.57 minus j 0.19, and path 2, that is because of alpha 2 and tau 2, we have 0.18 and minus j 0.24. 0.18 minus j 0.24, and alpha 3 tau 3, which is minus 0.19 and what is that, plus j 0.06, right?
Yes.
Right, yeah. So what we are supposed to do is that there is a summation term here. See, these are the individual components, that is alpha I into e raised to minus, these are alpha I e raised to minus j 2 pi fc tau I terms, right? These are these individual terms, and what we are supposed to do is we have to add all the terms, right? So please add. What is the answer?
So
Yes,
1.15 plus J 0.44.
j 0.44. Yes. Okay, so this term corresponds to summation alpha I e raised to minus j 2 pi fc tau I, right? And in order to get the final answer, you have to multiply this term with u of t. Just write a term into u of t. That's it. Into u of t. Okay, so hope it is clear. Any doubt in these examples?
No, sir.
Is it clear?
Yes, sir.
Yeah, and the textbook I used is what is the name? Modern Wireless Communication Systems by Aditya Jagannathan. Okay, so I got this beautiful examples from that textbook, and yeah, that's it. Hope there is no doubt. So we'll end today's class, and I'll need two more classes to finish this chapter, and then I'll pass on. And tomorrow, I mean, in next class, we'll be seeing wideband channels. Okay, thank you then.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir. Thank you, thank you, thank you.